July 2026, the internet announced that an AI had killed an 87-year-old math problem. The Jacobian Conjecture had resisted mathematicians since 1939. Then an explicit counterexample appeared, credited to work involving an anthropic model called Fable. The formula checked out. Independent proof systems verified it. Leading mathematicians began explaining why it worked. But the public record does not show that an AI independently solved the problem. We do not have the prompts, failed attempts, tools, compute, or precise division of labor, and the difficult two-dimensional case remains open. These qualifications do not make the event less important. They reveal the real lesson. AI may be moving beyond automated work whose answer we already know. It may also help experts search through problems whose answer nobody knows yet. That makes this an R&D story. Look past the headline and ask which part of your own research process AI could improve. In July 2026, an AI-assisted counterexample reportedly overturned the Jacobian conjecture. Here is what was actually proved. Imagine a transformation of space. At every individual point, it behaves properly. It does not flatten a direction or crush nearby points together. Mathematicians capture that local behavior with the Jacobian determinant. The Jacobian conjecture said for a polynomial transformation, a non-zero constant determinant should force something much stronger. The transformation should have a global polynomial inverse. Informally, if it behaves correctly everywhere locally, it should not fold different parts of space into the same place. That claim survived since 1939. Then, mathematician Levent Alpoj published a three-dimensional polynomial map and credited Fable with working on it. You don't need to memorize the formula. Two finite checks matter. First, calculate the Jacobian determinant. It simplifies exactly to -2, so the map satisfies the conjecture's local condition everywhere. Second, substitute three direct distinct points. All three produce the same output, so the map is not one-to-one. It cannot have an inverse. That is enough to disprove a universal claim. A proof would be needed to cover every eligible map. A disproof needs one map that satisfies the assumptions and breaks the conclusion. The result is striking because the hard part was finding the object, not checking it. Exact symbolic calculation can verify the determinant. Direct substitution verifies the collision. Independent teams then encoded the argument in Isabelle and Lean, where small trusted kernels checked the formal proof. There is an important boundary. The map disproves the conjecture in 3 dimensions. Adding unused identity coordinates extends the failure to every higher dimension. But it does not settle dimension 2. That planar case remains open. So the Jacobian conjecture is dead, is defensible for the standard all dimensions claim. It is also an incomplete headline. The most difficult surviving case is still alive. When a breakthrough headline appears, check the exact claim, the verification, and what remains unresolved. The AI-assisted Jacobian counterexample is mathematically reproducible. The AI discovery process is not. The public evidence supports several strong claims. Fable was credited with working on the problem. A compact, correct counterexample emerged. Exact calculations checked the decisive facts. Independent formal systems verified them. Mathematicians have since explained the geometry and produced broader families of examples. But the public evidence does not tell us how the original search happened. We do not know the first prompt. We do not know whether the model started from the raw conjecture, an older construction, a human-supplied template, or a partially developed candidate. We do not know which external tools we used, how many failed attempts came first, how much intervention occurred, or whether another researcher could reproduce the discovery with the public product. That makes 2 different kinds of reproducibility. Result reproducibility asks, can another person check that this object works? Here, the answer is yes. Process reproducibility asks, can another person follow the disclosed method and obtain a comparable discovery? Here, the public record is not sufficient. This is not a reason to pretend the AI contribution was trivial. Humans also make discoveries through paths that are hard to reconstruct. But AI systems create a particular temptation. A short attribution gets expanded into a detailed story about autonomous research, brute force, symbolic tools, and machine insight. Those details may be plausible. Plausibility is not evidence. The responsible conclusion is narrower. An AI-assisted interaction produced a remarkable research object. The object is correct. The precise division of a discovery labor remains unknown. For a business, that boundary is not academic. If you want to improve an R&D process, the final answer is not the only asset. You need the path, the prior knowledge, hypothesis, candidates, failed tests, tools, model versions, observations, and decisions. Otherwise, the organization may process a result without possessing a repeatable capability. For your own AI-assisted path, preserve the path, not only the answer. The AI-assisted Jacobian counterexample points to a business opportunity beyond ordinary automation. Most business uses of generative AI still automate the known. Draft this email, summarize this document, classify this request, write code that meets this specification. The desired answer is understood in advance. Consistency is valuable. Variance is usually a defect. Research is different. Its purpose is to resolve something the organization does not know yet. In that setting, a model producing several plausible candidates may be useful. It can search literature, compare prior work, suggest hypotheses, generate designs, write experimental code, analyze results, or expose an explanation an expert had not considered. But the generative breadth creates value only when weak candidates can be rejected reliably. In the Jacobian case, the candidate is unusual, but the rejection test is cheap and exact. Calculate the determinant, substitute the points. The verification cost is tiny compared with the cost of searching blindly through possible polynomial maps. That relationship is the business opportunity. If AI makes candidate generation cheaper and your company can define a reliable test, you may be able to explore more of the design space without multiplying expert headcount or physical experiments at the same rate. This could apply to materials, engineering, product design, process development, technical due diligence, clinical or regulatory evidence, or any domain where specialists search before a decisive test or decision. It does not apply everywhere. If the real bottleneck is lab capability, approvals, missing data, or a commercial choice leaders are avoiding, a language model will not remove it. And if a bad candidate is expensive or dangerous to test, increasing candidate volume may make the process worse. So the first strategic question is not, where can we add AI? Find one place where experts spend expensive time searching before a trustworthy test can occur. AI-assisted research becomes useful only when generation sits inside an evidence and decision system. This is not abstract for me. In a current engagement, I'm helping build an AI-assisted evidence review process for a regulated Australian organization. The useful design is not an autonomous decision maker. It helps authorized experts interrogate complex document packs, trace an answer back to its source, identify when the available evidence is insufficient, and retain the final decision with the accountable human. That sounds less dramatic than AI solving a famous math problem. It is also what makes the system useful in consequential work. The evidence has to come from authorized material. A citation has to open the source an expert can inspect. Missing evidence needs to produce an explicit boundary, not a confident invention. Retrieval, generation, validation, and evaluation need to be separable. A model change needs regression testing, not faith that a higher benchmark score will improve the real workflow. Permissions, source versions, privacy, security, and auditability are not decorations added after the interesting AI work. They are part of the product, and the pilot has to earn the right to progress. A good demonstration is not production evidence. The organization needs representative cases, acceptance thresholds, failure analysis, accountable owners, and explicit decisions about what the system may or may not do. This engagement is not proof that AI has already accelerated scientific discovery. It illustrates the operating systems around research. Faster search and synthesis inside a process built for verification. The same pattern applies whether AI is reviewing evidence, proposing a design, generating experimental code, or suggesting a hypothesis. The candidate can come from the model. Authority cannot. Before deploying AI in consequential research, decide where evidence ends and human authority begins. If your company wants to test AI-assisted R&D, start with the research loop, not the model. First, what valuable uncertainty are you trying to resolve? Name the product, material, process, engineering, scientific, evidence, or service question. Separate the commercial objective from the unknown technical outcome. Use AI to improve innovation is not a research question. Second, where is the search bottleneck? Map the current process. Are experts losing time finding prior work, reconciling evidence, generating candidate designs, writing experimental code, interpreting results, or documenting decisions? Do not insert AI where the real constraint is a machine, approval, missing data set, or unclear strategy. Third, what bounded role should AI play? Give it one research function: retrieve evidence, generate candidates, propose testable hypotheses, create an experimental artifact, analyze a defined result. Do not ask one model to silently perform the whole research lifecycle. Fourth, how will you reject a bad answer? Define a test before you scale generation. Maybe an exact calculation, simulation, benchmark, physical experiment, field trial, expert review, formal method, or independent replication. The cost and reliability of this rejection mechanism determines whether broad AI search is economically useful. Fifth, what must you record? Keep the prior knowledge, unresolved uncertainty, hypothesis, model instructions, candidate outputs, tools and versions, experimental design, observations, failures, evaluation conclusions, expenditure, approval, and decision gates. Failed candidates are part of the research asset. Without them, the company keeps the answer but loses the learning. Sixth, what evidence justifies the next investment? Decide what allows the project to continue, change direction, engage a research partner, begin a regulated trial, commercialize, or stop. A failed hypothesis may be valuable. An unmeasured pilot is not. Put these questions together and 5 imperatives emerge. Own the question. The business defines the uncertainty and consequence of getting it wrong. Expand the search. Use AI where breadth, synthesis, or iteration can reduce the cost of exploring the unknown. Define the test. Know how a candidate will be rejected or accepted. Preserve the evidence. Keep the sources, experiments, model history, failures, evaluations, and conclusions. Keep the decision human. Experts remain responsible for interpretation, safety, commercial judgment, and the next allocation of capital. That is meaningful human control. It is not a person ceremonially approving an opaque answer. It's an organization owning the structure by which an answer becomes trustworthy. Write down those 6 answers before you evaluate a model, supplier, or funding program. Australian businesses exploring AI-assisted R&D have several possible support pathways, but funding should follow project design. Each pathway supports a different stage and creates different obligations. The National R&D Tax Incentive is the broadest mechanism. Under the current guidance, eligible core R&D work is not simply work that feels innovative or technically difficult. It seeks new knowledge. The outcome cannot be known in advance, and the company follows a systematic progression: hypothesis, experiment, observation, evaluation, and a logical conclusion. The official AI and software guidance is especially relevant. Routine implementation, testing without hypothesis, or choosing among known options does not automatically become core R&D because a model is involved. In New South Wales, Tech Vouchers illustrates a different route. An eligible SME can work with a participating publicly funded research organization and receive match support for a product with a measurable commercialization outcome. The useful idea is collaboration. The company brings the industry problem in the commercial context, the research partner brings expertise, facilities, or validation the business may not sensibly build itself. Larger Commonwealth and New South Wales programs can support industry-led research or commercialization at particular stages, but the rounds discussed in this research are closed, competitive, matched, repayable, or tightly limited by sector, location, maturity, and project type. They are policy signals, not a promise of available money. So don't begin with a grant announcement and reverse engineer an AI project to fit it. Design a research project worth doing without a grant. Then get qualified advice and ask whether current tax incentive, research partnership, or funding program can accelerate it. Don't begin your AI-assisted R&D program by buying a research program. Choose one recurring point where expensive experts search or synthesize before a test or decision. Record the current elapsed time, expert effort, rework, evidence gaps, and cost of delay. Then define the boundary. Which sources are authoritative? Which data is permitted? What exact test rejects a bad candidate? Which human owns acceptance? Run the AI-assisted process against the representative past case or low-consequence live work. Measure retrieval quality, candidate quality, unsupported claims, failed test rate, expert review time, cost, and traceability separately. Keep the useful assets, the evidence corpus, hypothesis, test cases, evaluation data, interfaces, control, and decision record. These should survive a model of vendor change. Scale only when the process resolves uncertainty faster, cheaper, or with better evidence at an acceptable level of risk. Choose one uncertainty worth resolving and write down the test before you choose the model. The Jacobian counterexample does not prove an AI can replace a research team. It shows a more useful possibility. AI can help produce an unlikely candidate. Exact tools and experiments can test it. Experts can interpret it, and an organization can turn the result into reusable knowledge. Let the model search, compare, and generate. Keep control of the evidence, tests, failures, and next investment decision. Own the question, expand the search, verify the answer.